You might remember these notions from the first lesson. There we defined them informally, and now we have a definition of them within our language sentential logic. The bold letters are meta variables, so they can stand for any atomic sentence, or any sentence, not atomic, atomic or composite sentence of sentential logic. So bold P is any sentence of sentential logic. And P is a tautology if and only if it has the value T. It is true for any truth value assignment.
What's meant when you do the IFF, the if? What is that?
This is an abbreviation for if and only if. It's a meta language biconditional. This means that we can go both ways. If P is a tautology, then it has the value T for any truth value assignment. And the other way around, if P is true for any truth value assignment, then it is a tautology. The second one says that P is a contradiction if and only if not P is a tautology, which amounts to saying that P has the value F, P is false for any truth value assignment. P is contingent if and only if it is true for some truth value assignments and it is false for other truth value assignments. P and Q are equivalent if and only if they have the same truth value for any truth value assignment. So when we do the truth table, in any row, they will have the same truth values. P and Q will have the same truth values in any row. And now, let us say that the question is whether P is a tautology. And I find one truth value assignment. In other words, I find one row in the truth table for P where P is false. Is that line enough? Is it conclusive to give an answer whether P is a tautology or not? So I found one row where P is false. So if I find one line where P is false, I don't need to do the whole truth table. That's the shortcut I was talking about. If I find one line where P is true, then I don't need to check whether P is a contradiction. But to show that P is contingent, I need either to do the whole truth table or I need to do two lines. One where P is true, the other where P is false. Let me start with a simpler example, and then I will write one to explicitly answer what you asked me. What do you see now on the screen? Does it say shortened truth tables? They're called partial in the textbook. So suppose that the task is to show that this formula is not a tautology. Well, I will try to see if it is possible that the formula is false. So I will suppose that under the main connective, which is the disjunction, I could put an F. If I can fill in the rest of this line in a consistent way, then I do have an answer. If the whole line can be filled in consistently, then the formula is not a tautology. What does it mean that it is consistent? It means that I fill in the rest of the fields so that each atomic formula, in this case we have only one, has the same truth value throughout the line. The truth values for atomic formula change in the columns and they stay the same in the rows. If we say that B is false in one row, then it must be false throughout that row. It cannot change. Do we agree about that? What does it mean that the disjunction is false? It means that both disjuncts are false. The main connective is this, the disjunction. If a disjunction is false, as I supposed here, then both disjuncts are false. Where are the disjuncts? Node B is one.
And then the,
And
the whole parentheses is the other.
Exactly. Okay, so this is where we are. We make an assumption. We don't know yet whether it's possible or not, but we make an assumption that the whole thing is false, and we put an F here. That's an assumption. Why do I make that assumption? Because it gives me a conclusive answer to the question. It's enough to find one line to conclude that the formula is not a tautology if it's false there. If I find a line where the formula is true, it's still not enough to infer that it is a tautology because it could be contingent. So this is conclusive, and having this whole formula true is not conclusive. Our assumption says that the formula, the disjunction is false, which means if you need to have a look at the basic truth tables on page 150, you can do that. Disjunction is false only in one case, if both disjuncts are false. And these are the disjuncts. And where do I put their truth value? It's here, because here is the main connective for the left disjunct, and here is the main connective for the right disjunct. We said both need to be false, so we will have this. And I keep on doing whatever is left to see whether the whole line is consistent. And again, consistent means that B is assigned the same value throughout. If it is sometimes true, sometimes false, that's a contradiction. Okay, what is the easiest thing to do? We have the negation of B. It is false, so B itself must be the opposite. B is true.
the other B is true because the first B is true?
It has to be, but if this formula leads me to the other assignment, then it's a contradiction. So let us see what we have here. We have a conjunction, and that conjunction is false. And these are three possibilities. Either the first is false, the other is true. The first is false, the other true. The first true, the other false, or both false. So I need to do a fork and do three lines, but I'll try to avoid that. In other words, I can use what I have here. So here I finally got truth value of an atomic letter. And instead of doing the fork for the right formula, I can use this, rewrite T wherever B occurs, and see whether this is consistent. So we put a T under B, and now we need to see whether we have everything consistent here, because on the left side we already did everything we could. So if B is true here, its negation must be false. Is everything consistent here? Yes, we have T and F, and this is false. So the line is consistent. It means that we managed to find one line, one truth value assignment, where the formula is false. And this is conclusive. We can answer the question now. The formula is not a tautology. To be a tautology, it has to be true for each truth value assignment. Well, it is not true for this one, so it is not a tautology. Let me do another example where we get a contradiction. If it's not a tautology, it can be either a contradiction or a contingent formula. I'm going back to my slides. This is not exactly the question Monique asked before we started the short tables, but it is close. We have a formula and we need to show that it is not a contradiction. What can it be? Either a tautology or a contingent formula. Now we have a choice to do either a short table or the whole table. This one will have at least 2 lines because we will have some forks along the line. Okay, why did I start this way? The question is whether this equivalence or this biconditional is not a contradiction. If I manage to find one truth value assignment that makes the formula true, then this is conclusive. I have the answer. A contradiction is false throughout. It's false for all truth value assignments. And if we manage to find one truth value assignment where it is true, then it is not a contradiction. So if I started with F, it would not be a conclusive thing, whatever I end up with when I fill in the rest of the fields. But filling in the rest of the fields, starting with T, will give me a conclusive answer. Okay, what does it mean that the biconditional is true? It means that the subformula on the left and on the right have the same truth value. So they are either true, both of them, for a single truth value assignment, or they're false for some other truth value assignment. It's enough for us to do one of these 2 lines. Each of them will give us the conclusive answer. So let us start with the bottom one. It says that the conditional on the left is false and that the conditional on the right is false. If you check the basic truth table for conditionals on page 150, you see that conditionals are false in only one case, when the antecedent, the first one, is true and the consequent is false. So here you see the first one true, the second one false, and here the first one true, the second one false. Is this okay? Is it consistent? I believe you will be clear when I explain this
Oh,
line. This is where we started. We had an assumption about the whole formula. This is the main connective for the whole formula. This assumption had some consequences, and we wrote down those consequences in these columns. Then we chose the bottom one to work on, this one. We chose the bottom one to work on, and we had to see what does it mean if I put an F here and I put an F here. If I put those F's, then I have to do this and this. And the consequences of this F is this and this. And this leads to contradiction. Which one it is? The atomic formula A is true, and the atomic formula A is false. So this is not a truth value assignment.
Okay. And you chose to do that second row because in the first row, if you were doing a contingent with true as that connector, there would be more options. You would have to veer out more.
Yes, I have more work to do, so I hoped that I could get away with doing the bottom line only. And I did not get away with the bottom line because I ended up with a contradiction. So I have to go back to the first line. So what you will see on the next slide, the bottom line will be erased because we did everything we could. We don't need it anymore. We go back to the first line, and now we have a fork because there are 3 possibilities for true conditionals. We say that the conditional is true, and we have 3 cases, and here again we have a conditional. So we have three possibilities, and they're all written down here. We started with the left one, and the consequence of this truth might be that both subformulae are true, or the first one can be false, the second one true, or both false. Now, if I write the same values on the right side, so if in each row I write the same truth value for A wherever A occurs, and the same value for B wherever B occurs, I will end up with a line that is either consistent or not. So let me see, if we do the middle line, we end up with a contradiction. In this case, I wanted to show you a contradiction. And in this case, the contradiction is different because it's not the atomic formula that are both true and false. It's this conditional that is both true and false. Here we say that it is true, but with this combination, T and F, it cannot be true, it must be false. It's the one case in the basic truth table where the conditional is false.